Hi, everybody. We're going to continue our discussion of section 4.2 on the node voltage method. And in this section, I want to talk about the node voltage method and Ohm's law. Now, Ohm's law, as you'll recall, is suppose that you have a resistor here and you place a voltage across the resistor and you happen to draw a current. Now we know the relationship between the voltage, resistance, and the current is an algebraic one, and it's that V is equal to plus I times R. Notice that the passive sign convention here has been respected. So respect passive sign convention. That's one of the reasons why I have a positive sign here as opposed to negative. Now, the voltage that we have, this one, is a terminal voltage, right? And we need to rewrite Ohm's law to incorporate the new node voltages that we have just defined. So before we can do that, one of the things that we'll have to do is somewhere else in the circuit, and doesn't really matter where in the circuit, there is going to be a reference node, a ground node. And the reference voltage there happens to be 0. Similarly, just for simplicity, I want to make a distinction between this node and that node. So the way I can make a distinction between those two things is I can give them names. I'm actually going to say that this is node 1, whoops, and this one over here is node 2. Now, one of the things that I can do is, now that I have these nodes named, 1 and 2, I can actually define the node voltages for each one. So the node voltage for node 1, I'm going to call V1, but remember the definition of node voltage. It is the voltage rise from the non-reference node up to the node in question. That means that if I start at my reference node and I go through some path through my circuit, and it doesn't matter what path it is, I eventually end up over here. If that node voltage V1 is going to be properly defined, then it must have been a voltage rise, which means that it must have that particular polarity. Similarly, the node voltage V2, I have to start somewhere else, going from the reference node somewhere else through the circuit, and it doesn't matter where or what path I follow, right? I can follow this path like this, and I have to go through a voltage rise to get to that node voltage V2. That means that my polarity must look like this. Now, one of the things that I can do as well is I can start at my reference node and then define a loop. So here I'm running out of colors, but I need to keep these here. So I'm going to define a loop that goes arbitrarily through all of those elements and ends up back at the reference node. So one of the things that KVL tells me around this loop that I have just defined is that the sum of the voltages around this loop must add up to 0. So if I start down here at my reference node and I go up to node number 1, notice that the first sign that I hit is this minus sign. So into KVL goes minus V1. Right? I then go from there to there through my loop, and according to my terminal voltage, notice that this is the sign that I hit first. Therefore, into KVL goes plus V. I then am at this node, and I go back down to my reference node. Notice that the sign that I hit when I hit V2 is positive. So I then have plus V2, like this, and this must add up to 0. So the sum of these voltages must add up to 0. Notice that one of the things that I can do here is I can actually solve for my terminal voltage V, right? In which case I get V is equal to V1 minus V2, and now I can use Ohm's law. Why? Because this voltage and that voltage are the same thing, right? So equating those two things, or using Ohm's law, we get that IR is equal to V1 minus V2, or solving for I, that we have V1 minus V2 over R. This is the modified version of Ohm's law that incorporates these new node voltages. One very important thing that I want to point out is that the ordering of V1 and V2 is very important here, right? It really has to do with the direction of the current that happens to be flowing. The current started at node 1, went through the resistor, ended up at element 2. So wherever the current starts, that's what goes first. Wherever the current ends, that's where that happens to be incorporated. So there is a sign here, a directionality that must be respected whenever you incorporate these new node voltages into Ohm's law. And we'll see various examples of this as we start using the node voltage method.